I don't know. I have issues problem. I always think I will come back. Oh, well, before, yeah, but you know, you think I want to build a garage. Here I found like a blueprint for how to build a garage. It's hard to find. You have to pay money. So I should close it. But I do close a lot of things, but still.
Are you building a canoe?
No, it's like a tiny wooden boat with my son. It's just instructions official. Oh, somehow now the garage isn't talking. Yeah, it's a weird habit. I don't know. How do you guys manage your tabs? You just close them?
Oh, sometimes I just close everything without looking at what's happening.
Sometimes I let the kernel panic.
Like you'll validate your full cache. And
I know. Then I have a bad day then. That's scrambling. Okay, so what I wanted to do today, which is hopefully that's the last for real class on interrupts. So talk about this new combination, or like essentially up-to-date combination of interrupt controllers. Because if I talked a little bit about legacy programmable interrupt controller, which Philip also covers in his blog post, which we discussed last time, that's fine, but really no one does it this way. So I argue that you should go and read his blog post, but really the way it's done now is this combination of local advanced programmable interrupt controller, LAPIC, and IO epic advanced programmable interrupt controller. And the idea here is that like each core will have its own LAPIC, right? So, and there will be one IO epic in a system. I mean, maybe there are cases where multiple, but I only heard of when it has one. But essentially, so one local epic per core, right? And it does handle, and we will just go and take a look at all these possible cases, but really it just like some of those interrupts are local, so you can configure multiple timers. Then you'll get those interrupts from a timer. Thermal events when the CPU is overheating, like when you use profilers like perf, when you say, send me an interrupt after 100,000 instructions, for example. So this is that you will receive it from LAPIC. And essentially this is, I mean, do you guys even know how those profilers work, or how do you identify the hotspot in your system? Do you ever use perf? No, never.
I've used it.
But do you know how it works? No, like for example, you've seen those diagrams where you say like, I don't know, like where you have like a stack of functions.
Yeah.
Or like there are multiple ways to represent it, but roughly speaking, you say like, well, function foo takes so many cycles in your program. So the way it works is that the CPU maintains a set of programmable counters. I think it's literally just 4, and you can program them to count specific events. So for example, just cycles which passed, or for example, number of load and store instructions, and for example, number of branch instructions, right? Or other events like cache misses, cache hits, stuff like that, right? And so it's fine. So typically what you do is that you say, look, if I just simply want to have a distribution of like attribute like number of cycles or percentage of cycles to each function in my program, you say, look, please send me an interrupt, and you pick a number here. You can pick a reasonably fine grained number like 10,000 cycles, and there is a programmable timer. No, actually, it's not programmable. Timestamp counter, which increments by 1 every cycle of the CPU, right? Every time you execute like not instruction, but it counts, so ticks, right? And so this counter will reach these 10,000 cycles and then send you an interrupt, right? At this point in your operating system, now you know how the interrupts work, right? So your interrupt handler, which is configured to handle this interrupt, essentially remember the interrupt frame, right? There will be instruction counter, and you say, look, this instruction counter points to the location inside a function foo. And you, roughly speaking, increment the stats by 1. And next time maybe it will be bar. And next time it will be something else, like pause. But statistically, if you run the program for long enough, and if this counter is fine enough, then you will get this distribution. So you will have proportionally, I don't know, 90 episodes when you found like instruction pointer inside 4. I don't know if there's like 60 times inside whatever function, 30 times inside bar, stuff like that. So this is how essentially no instrumentation of the program is required. This profiling is statistical because you say statistical, meaning that on average, according to some whatever mathematical formulas, you will get this distribution which approximates the real time spent in each of those functions, right? So this is part of this performance monitoring interface exposed by the CPU. Does it make sense? But it's kind of a very powerful tool because it allows you to explore really sophisticated conditions in the programs. And as I mentioned, you typically Intel exposes something like just 4 counters, but if you want to observe different events, so for example, this is just time spent inside each function. But for example, you want to say like, give me also a distribution of cache misses in each function. Then you, for example, say either you program the second counter to give you cache misses, right? And Intel publishes the different events which it can count and monitor, right? But if you run out of these 4, then you also kind of like your kernel implements the logic of rotating those counters and collecting those events periodically. So if, for example, if you want to collect 8 counters, you will alternate between these 4, then program another 4, collect, back again, stuff like that. And there are like different approaches for how to alternate. But essentially you can collect a variety of statistics, and this will be handled by local APIC. Make sense? It's kind of worth knowing because like we do a lot of performance analysis in my team. And that's essentially Perf is a Linux interface to this counters, and Intel has their own powerful profiler, which is called vTune. And vTune essentially is a front end, which Intel maintains a driver and a software stack, which configures the driver and the kernel to like collect specific counters for specific exploration, meaning that Intel helps you to hint. You don't have to say, I want a specific counter which counts like L2 misses. If you say, look, I want to understand how what is the memory profile of my program, like memory misses, stalls caused by memory misses and stuff like that, stall cycles of the CPU. Then it just will collect automatically a bunch of related counters and then just show you as a GUI. It's quite powerful actually. So like I recommend you to at some point look at this, right? Again, compared to this legacy pick, I'm not sure that legacy pick was allowing assigning priority to interrupts, but here you actually can assign priority, and essentially different, like if 2 interrupt conditions exist, one of them will be delivered first according to how you program this thing. Another interesting feature is that it allows you to send interrupts between CPU cores, right? So essentially, and we'll see more of it, but the idea is that in many cases, you want to be able to preempt execution of another core from one core, preempt execution of another. And this is called an inter-processor interrupt. And this is essentially those, like, logic allows you to do it. If I ask a question under, like, can someone give me an example why this inter-processor interrupt is useful? It's a tricky business, but yeah, sure.
I know in some applications, you can designate a core as the interrupt handler code. So handling the interrupt does not affect it.
We'll get to it in a second as well, but most frequent case for sending an interprocessor interrupt in a modern system like Linux, what it will.
Priority, and it wants to use the second core to handle one of them, so it can like interrupt the thing which is running on core 2 and kind of ask the process.
You mean like implement some scheduling event where you say, look, I believe that I want to have some, like, imagine you're running process 1. Imagine it, I don't know, like some low priority things like, I don't know, crypto mining, something like that. This core, for example, says, look, I know that there's P2 now, and I want to add you to your scheduling queue. Yeah, that's a good case, but I agree. So you can send an API, then this gets into the kernel, looks at the scheduling queue, starts running P2. Good example, but the most canonical, very notorious example of sending interprocessor interrupts, which slows everything down, and everyone is like absolutely crazy about it. Have you heard of TLB shutdown at all? So does anyone know what it means?
It's clearing the translation.
Correct. So imagine you run a process P1. I don't know, maybe it's a web browser or something, like anything. It has 2 threads of execution, P1, P2, right? Imagine P1 executes something like mmap, just maps a page, right? Sure, like this guy has CR3, points to the page table, right? We walk at the mapping, so this is mapped to some physical page, right? Next time this guy accesses this page, since it probably shares the same, so this one has a CR3, right? Each core will have its own control register 3, also points to the root of the page table, also walks the page table, reads this entry, successfully accesses, right? So this is all automatic, right? So CPU designers handle it for us. Imagine now this guy does unmap. Think I want to remove this page from my page table. Now what do we have to do? Because you say, look, okay, sure, if I walk this page table, I will remove this entry. That's fine. How does this change? Will this change be reflected on the other core or not?
If the other core reads, like walks the page table, then it should work out fine.
Yeah.
But again, like if it uses the cache translation.
Yeah, TLB. So do we know TLB? Translation Lucas Ed buffer. Do we remember what it is?
Stores translation so that it doesn't walk every time.
Correct, absolutely. So TLB is also per core, right? So the first time we map a page, we walk the page table, this entry was added to this TLB. This core will have its own TLB. And again, the first time this thread accesses virtual memory, this virtual to physical translation was added to this TLB, P2P, right? Now we have a problem. TLBs are not cache coherent. The moment you remove this entry, you have to flush the entry from your local TLB, but also flush the entries of all the CPUs where other threads of this address space are running, right? How to do that? That's essentially you sending interprocessor interrupt. There might be multiple synchronization schemes, like you can. Essentially, the point is that nmap cannot return until all these entries are unmapped on all the CPUs. You can come up with a different synchronization scheme, like checking for certain messages and then like flushing to TLB, but most commonly implemented method, which is not ideal, is to send an interprocessor interrupt and essentially say, please look up this entry, flush the TLB, and then mmap can return. Right, so that's the most common reason, and this is expensive. So sending an interprocessor interrupt and flushing TLBs because you preempt execution on this thread. So processes which will have frequent modifications to the address space and specifically unmapping something from the address space will suffer from overhead of TLB shootdowns.
Just a quick clarification, does the TLB shootdown only remove the entries related to that address space, or does it clear the entire?
Modern CPUs allow you to flush a specific entry. So otherwise you will clear the TLB, and that's like an even bigger performance penalty, right? So typically you just, yeah, like there is a CPU has an interface saying, okay, flush one entry, right? Okay, so TLB shutdowns. Okay. And in general, what happens is that it maintains this local vector table. We'll talk a little bit about it, but it essentially like maps hardware interrupts to local interrupt vectors, right? Okay, sure. Local APIC per core does those things. Like IO APIC, the second part of this bundle, essentially handles external devices. And essentially everything what we talked about, like keyboard, network interfaces, everything what we talked about in this legacy programmable interrupt controller will be managed by this IO APIC, right? So it's, if in the past it was like physical wires, now everything is like real messages on this network inside those controllers, so nothing gets lost, stuff like that, right? But essentially, for example, and I will explain it in a second, but there might be something like your keyboard IRQ will be mapped by BIOS, the specific IO PIC, they call it a pin, that this is controlled by, roughly speaking, sometimes it's programmable, but roughly speaking, controlled by the BIOS. But after that, you essentially maintain this table, which essentially this goes to a specific LAPIC, so you can actually configure either a specific core, like APIC ID 0, for example, or there is also support for this round robin, and you can actually send the interrupts to the CPU computes a specific, I forgot exactly how the scheduling discipline works, but it kind of picks the one which was not used recently and kind of fairly distributes interrupts between local advanced programmable controllers, meaning between like the same interrupt will be rotating across all the cores, and then LAPIC, for example, maps it to like vector 21. And all of it is configurable. Even this bias link is configurable, but not always, because some biases say, look, we're not going to allow you to remap like a keyboard interrupt, but and again, those details I don't know really. But so sometimes it appears at kind of like as a fixed mapping, but typically it's configurable. Just one more time, like wanted to talk through these different different sources from where the interrupt can show up at the local advanced programmable interrupt controller, right? So like this local sources like timer interrupt, terminal sensors, we talked about it, interprocessor interrupts, or from the APIC, from the IO APIC essentially. So three main reasons, right? So like real external event from a device routed from the IO APIC, interprocessor interrupts from other cores, and local sources from local timers, thermal events, and performance counters. There's these two funky additional pins, which are called link 0, link 1, which stands for local interrupt 0 and local interrupt 1. And those are kind of like legacy interfaces. So essentially, like if this is your legacy programmable interrupt controller, this new bundle, new IO APIC plus LAPIC, they can work and pretend as if they were like this local as a legacy PIC, right? And so essentially this legacy PIC had two interfaces: normal interrupts from devices, which were maskable, and non-maskable pin. And those essentially link 0, link 1 kind of allow you to implement or emulate legacy mode. Essentially, I think link 0 becomes like kind of logically becomes an interrupt from an external device, and link 1 becomes a non-maskable interrupt, right? So there is the special mode which like essentially allow you to emulate this old PIC on top of those LAPIC and IO epic. And this is what, when Philip configures this system, I think this is what is happening, right? Because there is really no legacy pick. Makes sense? So essentially, just again, if you will see all these funky, weird names, and I just wanted to make sure that we have at least some understanding of what these are. So like 3 main sources, emulation of legacy interfaces. The funky part here is that you actually, they're fully programmable as well. You can like, I'm not an expert, but you can also program different events to be delivered through those lint 0, lint 1. So if you're not trying to emulate local legacy pick, then you can use those for routing other events. Let me just talk a little bit about it. So again, local events, right? So essentially, by the way, you can kind of configure, let me just find a slide, we have it here. There is a chance, no, I'm sorry, you can just simply configure the LAPIC and you'll get the local events. So like performance counters, timer, things like everything will be working, right? But anything from devices like keyboard, disk, network interfaces will not be delivered, right? Because there is no way for the IO epic to reach the CPU, right? Or vice versa, you can configure the IO epic and devices will be able to raise interrupts, like they say, assert the pins, but nothing will happen because in order to reach the CPU, IO epic first goes to LAPIC, LAPIC goes to the CPU, right? And then it just essentially triggers int 32 or something like that, right? So you have to configure both, right? This makes sense? A little weird. And as I said, like, since there are like 1 LAPIC per CPU, IO epic can deliver to different epics, to different LAPICs, right? So let's talk a little bit more about it. So local events like timer interrupts, and there are multiple different timers. Again, I'm not an expert in timers, but essentially like two main modes which people typically use are either the periodic timer, meaning it will deliver an interrupt every 10,000 whatever milliseconds or something, right? And it will try to keep track more accurately of like how the cycles map to this interface. Or you can configure a timer which says, I will run for some number of cycles and then please interrupt. It will allow you to implement a more flexible scheduling policy because you say, look, some things I like in some period of time, I want to like interrupts to come more frequently. I don't know why. Maybe you detect certain condition, and sometimes you don't care, and it's like flexible. It's pretty cool actually, because there is always this trade-off in the past. Like GUI systems supposedly should receive interrupts more frequently, so the human doesn't perceive a delay. Server machines, preferably less interrupts, just make sure that you don't waste a lot of time on processing interrupts, stuff like that, right? So this scheme is more flexible, so you can also think about it whether you can leverage it in any of whatever research tasks which you have, right? More or less, we talked more like about those sources. Interprocessor interrupts, I also, we discussed a little. So I say, okay, TLB shoot down, rescheduling is what Manwick was suggesting, or I forgot, or Soham, essentially the idea that you can send an interrupt and reshuffle your scheduling queue or something. But also what we will see when we program the system, these interprocessor interrupts are used to wake up application processors. When you're booting, one CPU is running, this one's drop CPU. And essentially everything else is left by the BIOS. It ran for a little bit, initialized the caches, stuff like that. So everything is working, but it is waiting for the operating system to receive this startup interprocessor interrupt, right? And so what we'll see when we will boot into the system that we will be running on a bootstrap, BSP bootstrap processor. And then at some point you reach a point in your code, and you've seen it in x86, where you will wake up other application processors which were like sitting there waiting. And this is done through this interface of interprocessor interrupts as well. This is the only interprocessor interrupt which x86 is using. So if I ask you a question, why x86 doesn't need TLB shutdowns? Killer question on the exam.
threads.
Doesn't have threads, right? Exactly. So meaning that if you do an unmap, you have a guarantee that no other threads are using the same address space concurrently on other CPUs. But x86 does clear the TLB entry. So it will locally flush, right? So this is why when we had, I don't know if you were in the version of this class where I was asking to build threads, but essentially I never mentioned TLB shoot down in the homework, but really it's incorrect. So any unmap breaks the address space, and then any other process can leverage it as an attack, right? But just make sure that you understand it. So
is the IO mapping mostly just a hardware software interface sort of, because it's mapping these physical pins to graphics and software?
looks like it, but I'm not like an architect, so I don't really know what's going on inside and why they decided to do. I know that it's honestly, I don't even know whether it's on chip. It might be like a system on chip, maybe it's on chip these days.
But typically it's one IO mapping for.
That was my impression, but that's a good question, and I don't know if you in a dual like two socket system,
Right.
whether you will have two IO APICs.
But lapping is per core.
LAPIC is per core. I can try to search real quick online, but and that's a great question, and I somehow didn't think of it. Okay, let's do ChatGPT real quick. Maybe it will tell me something, but or like whatever. Let's do this. Like
We can discuss this later as well.
yeah, okay, sure. But that's a good question, and I wanted to know the answer myself. So if someone finds it, yeah. There is Alex.
According to typically it's integrated.
Yeah, so two sockets and two IO APICs, and I have to initialize both. I don't know. Huh? Okay, yeah, but that's logical because nothing is on a motherboard anymore. Except that whatever, like what is it called, Southbridge or something. Okay, there's this funky thing which is hard to, again, worth knowing. I never touched it myself, but in the past there was this condition because this ISA, which stands for this industry standard architectures, it's like those IRQ lines from the keyboard, from the mouse, with physical wires. And the system was noisy, so electrically noisy. So it could accidentally deliver an interrupt where there was no actual interrupt, really was not raised, right? And so those programmable interrupt controllers had this spurious interrupt vector rate. So essentially mostly it was a hardware condition when you say, look, I don't really know what's going on. I will just deliver it to you and please resolve it somehow. And typically operating system was just acknowledging it and not doing much, right? Hoping that it will just be okay, right? But this thing still stayed in this architecture. And so you really need to like map this spurious interrupt thing to some vector, right? So today, however, all the systems are like they maintain reliable communication protocols. So it's mostly like a network, right? So it's all message-based interrupts. And so nothing is like electrically noisy. And typically this spurious condition occurs when you misconfigured the IO APIC. Essentially, there is some mismatch between the software configuration and what hardware is supposed to do. And then it raises it kind of like an exception, right? So anyway, you have to handle it, right? And there will be a register, this SVR register, and you will have to write a vector saying, okay, please deliver this interrupt when this condition happens, right? So again, just to make sure that when you see it, you will not get super surprised about it. So lint 0, lint 1 we discussed. So like, again, they were used to emulate a legacy PIC, but today you can use this, we will talk about it more, local vector table. Essentially, you can configure what to do with this interrupt, and you can essentially figure out the delivery mode and stuff like that, and which vector and stuff like that. So it's fully programmable, but Okay, maybe it's not as important today. So, okay, so IO Epic. So IO Epic, again, in my slides, I said it's on the chipset, but as you say, it's probably is on chip. So it's not on a motherboard, but most likely it's on the socket itself. Like I say, implemented inside of the CPU. Maybe I'm wrong here, right? But essentially, the idea is that what I wanted to say. The idea is that you maintain this table, and essentially, when the hardware raises a pin, kind of like, okay, a keyboard is pressed, you use this table, you as an operating system designer, to route it to a specific entry in the interrupt descriptor table. So you assign a specific vector, right? So when I was using a timer interrupt example, I remember interrupts from 0 to 31 are reserved by Intel as exceptions, right? And then timer was always mapped to 32. So technically speaking, you can map it to some other vector, right? Again, when you program this legacy pick, you can just shift, like I think all the IRQs are just like solidly shift by some offset, if I remember correctly. But here you can really remap. You can map all of them to one single vector. You can do whatever you want through this table, right? And I'll show you, we'll talk more that you can configure the delivery mode. So you can say, look, by the way, deliver it as a non-maskable interrupt. If you want to have your keyboard delivered as a non-maskable interrupt, you can do it. But then it will go through vector. Yes, if needed, you can do it. But also you can like fix, like there are delivery modes, this priorities, like the lowest priority fixed. I don't remember exactly what this means, but it essentially allows you to assign a priority to each interrupt, which allows you, like, if the multiple interrupts are raised while you're not handling them, then the highest priority will be delivered first, right? But it can also, most importantly, you can specify the ID of the LATIC where you want to send it, right? And in the past, the idea was, let's send everything to like 4.0, because it didn't scale very well, because the one of interrupts 4.0 will never run happily if you do this, right? And then essentially, now there are different schemes for how you want to, like, and there is a round robin scheme, which hardware supports as well. But you as a systems designer might choose to do something fancier and pick where you want to route interrupts. And maybe I haven't looked at it, but one could imagine that you might periodically reprogram the interrupt entries to make sure that you load balance or do certain quirks, right? But again, this last line is that IO Epic never sends anything to the CPU directly. It just goes through local advanced programmable interrupt controller. We talked about this. So for example, if you have a keyboard, someone presses the keyboard key, like somewhere machine BIOS programs it that there is a specific, like they say, line IRQ or interrupt pin, but essentially reaches IO Epic. IO Epic looks up this redirection table for pin 1, because IRQ1 is pin 1. The table says deliver this interrupt through vector x21 to LAPIC with ID 0, so it's core 0, right? And then IO Epic sends an interrupt message, like reaches LAPIC 0. LAPIC 0 sees the message, looks up, it's this local vector table, delivers vector 21 to the CPU. CPU, as we discussed, looks up the interrupt descriptor table entry number 21 and handles whatever all this interrupt transition happens, right? Makes sense? Okay. I had this question myself, how we can configure, whether we can configure the mapping between the devices, like actual keyboard and the IO Epic inputs, right? And there is this mechanism. I never touched it myself, but it does exist. So what is ACPI? Advanced something peripheral interface. It's part of the BIOS, but essentially it allows you to, or this multiple Epic description table allows you to change inputs from devices to pins, right? I never touched this myself, so never bothered, but it's nice to know that it's there, right? So you can reconfigure, so it's not strictly fixed, but again, for some legacy devices like keyboard, legacy mouse interface, PS2, many boards will not allow you to change the mapping, right? To change the mapping, right? Okay, cool. So we understand that, okay, somewhere like BIOS allows you to say IRQ1 for the keyboard. Maybe it will not allow us to do that, but maybe it will. And then after that, it's all IO ABIC, right? And I wanted to discuss this like round robin delivery mode. So essentially, in the IO ABIC, this redirection table, and I never really like listed the entries, just high level description. There are two things: destination mode and destination field. And destination mode, which is bit 11. If it's 0, then it's a physical mode. So in the destination field, there will be ABIC ID, right? So like CPU 0, for example. If the mode is logical, so this bit, destination mode bit is 1, then the destination field is a bit mask of CPUs in the logical cluster. So essentially, you can configure that the interrupt, the hardware will be like implementing the scheduling policy and kind of like implementing this round robin delivery mode for different CPUs. And it would be nice to play with this. I don't know if QMU faithfully emulates IO ABIC, but most likely they do, right? And so we can try and see that, you know, since we will start the bootstrap CPU, start multiple application processors, we can play a trick and say, look, let's make sure that this keyboard interrupt is delivered in this logical mode. Then see how it works, right? That whether like it will distribute it across all cores, right? So lowest priority literally means deliver with the lowest priority among everything else. And apparently, this is how you program this round robin. You set up this lowest priority, and then ABIC has a priority register. So the next interrupt is sent to the CPU with the currently lowest priority. And supposedly, over time, this achieved this round robin distribution. So what it means, don't exactly understand what it means, but apparently, if another interrupt is in flight, then that CPU will have some other CPU will be chosen for this, for the lowest priority. That's my understanding, but I don't know for sure, right? Okay, so if you essentially, if you want to do this trick, so you fill in the entry, delivery mode, lowest priority, destination mode, logical, destination field, the mask of all CPUs, which you want to receive the interrupt, and then ABIC automatically distributes the interrupts across the CPUs, right? So that's kind of a fun trick, but again, I'm not an expert in this field, but maybe there is a way, maybe there are cases where you say, look, I will program a system in such a funky way that I say that, for example, all interrupts from the network interface will be routed to a specific core. And I assume that this core will be running the network device driver and the network stack. And all the interrupts from the non-volatile memory controller, NVMe, will be routed to a different core. And this way you kind of, or even you can like split the system, saying if you have two network interfaces, you can say like, okay, sure, those masks will be different and you can receive interrupts on specific subset of cores. It's still, I would say, a research challenge to figure out the optimal routing, but you probably can. So for example, one example is that imagine you have a socket. Like, just for the sake of example, I'm drawing the machine with just two sockets, 4 cores in each, right? Right? If you remember, I was mentioning that PCI controller, which is also on board of this, like same silicon, connects to this PCI bus. you, for example, might have a network interface which sits here on this PCI bus. These two sockets will be connected with a cross-socket link on Intel is called UPI. What exactly? Does anyone remember what UPI stands for? Unified Bus Interconnect, I think. Here, there will be another PCI controller, and it will have PCI bus, and it may happen that you have a network interface on this PCI bus. There are papers about it. My friends were writing them, but logically you say, look, interrupts from this guy should probably be routed to this course, let's say 0, 1, 2, 3. And interrupts from this device should be routed to this course, whatever, 4, 5, 6, 7. Why is that? Because everything it's local, right? It doesn't make sense to cross this UPI link. The DMA, everything, if you will be trying to reach this device, it will be longer from those cores, right? So it makes sense, like if you're really careful about programming those last bits of performance, make sure that you understand that the systems which you're dealing with are distributed systems, and you can more carefully, and whatever, you can say machine learning. Okay, machine learning is a funky thing. Maybe, I don't know, network processing, anything. So anything with IO. And it can be, for example, network interfaces or NVMe, or storage interfaces, like this. But essentially, there are studies which say this locality of processing interrupts and just accessing devices can be beneficial in certain cases. Just make sure that you remember it. Like, if you absolutely, like, someone hires you to deliver the very last bits of performance, and honestly, no one will really know the answer how it should be done. So it will be your research goal to figure out what's the best setup. You'll have to fight Linux on the way. Well, that's another story, but at least you will know the story. Like when you know what is that you're fighting for, it's much easier to fight Linux. Or maybe you will have to build your own stuff. And then you at least start thinking in those terms.
So the destination field, for example, if I'm running a application which requires keyboard input, and that will only be running on one of the cores.
Yeah. No, let's say a keyboard is not connected to PCI. I forget exactly how it goes. It will do this ISA, whatever the bus I mentioned. And then let's say keyboard is attached here somehow. Right?
Yeah.
But it will be eventually, I think, attached to the PCI controller, but through some other buses.
Right.
Yeah.
But the keyboard interrupt will still be delivered to the IO APIC for processor 1. But if the application itself is switched out to a different port, that will have to update this redirection table to.
Okay, so great question. And to be honest, I mean, I get it. So it gets a little less interactive. It's a sleepy day today. So let's wake up for a second. I mean, to me, it's kind of almost natural, but it's nice to let someone answer what Soham is asking. Imagine someone configured, imagine for the sake of example that there is a IO APIC here, and maybe there is an IO APIC here, but we don't really care. But each of the cores will have LAPIC, and so on, right? And there is a table inside the IO APIC, and it says, look, from this pin whatever, pin, let's say 1, right? Because the example uses pin 1, probably pin 0 is a timer or something, I don't know. You say deliver it to core 3, right? So you, in the interrupt descriptor table, which is configured inside the interrupt descriptor table register of this core, right? You go ahead, and the mapping is that you send the interrupt number 33, for example, which is typical for the keyboard. So entry number 33 is picked here. You jump to the handler. Makes sense, right? And you start processing the keyboard. And imagine like application which is like your shell physically, which is waiting for this key, is running right now on core 5. So what's the connection here? How do we get from keyboard attached to IO APIC on, let's say, processor 0 to the 4.5, which is running in processor 1. Intel's like either cause the sockets or processors for whatever reason, and those are cores. So how does it work? You can tell me.
Just to clarify, in this example, also shell was earlier running on core 3.
No, like,
Shell was always running.
well, maybe it just rotates all over the place and the scheduler picks, like each of these cores will have a scheduler, right?
No, I'm just wondering why the IO epic.
Why did we configure to,
Yeah, the core 3.
maybe for the sake of example, maybe we did round robin scheme and that IOAP extends to all possible cores.
Okay.
Or maybe we just like, for whatever reason, we set 3 instead of 0, doesn't matter.
So why instead of 5 was?
Yeah, 5 I didn't want to touch because I'm not sure, I don't know whether this is, whether other processor will have its own epic. I should clarify this. Let's not go cross socket for now. But what's the connection? Why is it okay? And what does it even mean that shell wants an input from this keyboard? What's the connection between we received an interrupt here and shell, like you program the shell, right? So you know that you have to output command prompt and then whatever I typed, maybe a letter H or hello, and you have to put H here. How does it work? The person who answers can go home with an A. Okay, yeah. Kind of, yeah. I'm not saying no.
So when you type key, it'll go handler, and then it will write the standard input of the shell.
Kind of.
And the shell will get the character through there.
So remember, I mean, and it's up to you, and we'll be building this kernel, right? So, but let's use x86 as example. In x86, when shell says I wanna receive an input, you do something like a read from standard input, right? From 0. And okay, good luck to you. Maybe you're unlucky, and this 0 is not really connected to the keyboard, connected to something else. But let's assume everything is normal. And this 0, when you drop into the kernel, your like file descriptor table of this process, entry 0, instead of pointing to a file, will be pointing to something what implements a console in x86. On Linux, there will be something like TTI, and TTI is a mess. I never figured out how it works, but it's like emulates essentially the terminal or whatever, this connection to the keyboard. In x86, the code will check that, okay, it's not a file. So instead of trying to read from a file, what it will do, it will, I forget exactly how it's done, but essentially it will try to sleep on some event in the kernel. And then when the handler is involved, it will read H from the keyboard. And it will, I forget exactly how this plumbing is done, but roughly speaking, maybe there is some kind of a buffer here, right? And it will put this H into this buffer and wake up the sleeper, right? And then this gets unblocked, returns into your logic of your code here, and supposedly you run some kind of a loop. And at some point for this H to show up, you actually write to standard out. And then it's connected to, like, similar to how it was connected to the console. Here it will be connected not to a file, but like anything, let's say serial line or VGA, whatever it's there. And again, in modern system, it will be some PTI emulation, but essentially this, if it's VGA, it will go into this buffer. And if there is already this calling prompt, it will place H as an ASCII character, or Philip will render you a letter if you're using like a real, not VGA, but whatever it is using, like a frame buffer.
So I understand this and I see how it works, but if I now have 2 shell instances that are both waiting on you,
Yeah.
how does it map that? Like STDIN is common for everyone.
Right, so now you're asking a question, what if I'm running another shell?
And they're both in this sleep situation. So like the OS is a way of showing focus, like whatever shell.
Right.
Screens.
Yeah. So again, I don't know the details, but as you say, so the GUI environment will, like, remember, I don't have it, but on Linux you can switch into the console mode where you disable the GUI.
Right,
and
yeah,
like
yeah. That's the TBY.
Yeah, exactly. And so at this point, there will be some additional plumbing at which decides that there will be like multiple possible waiters and you choose among them. When you have a GUI somehow decides who gets the input based on the focus probably. And it's not hard to imagine how this can be built, how it's built in practice, I don't know. But that's the idea. So when you
Something like the current process.
no, like the focus is not the current process, it's the like really the like focus is decided, like GUI systems, they decide differently who gets the focus, right? So in Linux, you can just
Yeah,
hover but not even click.
I'm just like the focus window is the.
Yeah, it makes sense. So this demystifies all this story about how everything is delivered, right? And I forgot to my story was about performance, but we explained how everything works, how everything runs on a CPU. Of course, the critical hardware component which allows execution of this system is cache coherence, meaning that like if there is this variable h, which sits in some cache line, right? Which sits in a cache line, which stores a specific whatever physical memory, right? Because it can be mapped to different virtual addresses, but essentially the cache coherence protocol implements the fact that if I access this cache line from one core, I will get H. And if it gets written by the handler, which executed on a different core, for example, this handler executed on 3, right? It acquired this cache line in the exclusive mode, updated, like let's imagine it was empty originally. This guy writes H, and then the cache coherence protocol allows this guy to read H on another core, right? And the cache lines are bouncing back and forth, right? So that's important. That's how the system works. But the interrupts are underneath coherence, right? So it's kind of like a different, like they're routed through this IO epic, LAPIC. They are not coherent. The only coherence which you get is that maybe this interrupt descriptor register points to the same ID on all the cores, but maybe not. And you can say, look, this is where you can say that maybe this device will be using, if it's connected to this IO epic, and it can use like interrupt number, I don't know, 67 on this device is connected to this IO epic. Also can maybe use vector 67, and then maybe they no longer share the IDTs, but essentially each processor has its own IDT. If you feel like you're running out of entries in the IDT because you only have 256 entries, and you wanna maybe this device, just because everything, okay, so hold on, like what I wanted to explain is that those devices are so powerful that they can easily overwhelm a single core. Because imagine you're running like 100 Gbps interface. Like if you start sending interrupts on every packet, like if I remember correctly, in order to saturate 10 Gbps device with 1 kilobyte packets, which are like a typical size of a packet in the data center, then each packet arrives every 860 nanoseconds, or roughly multiplied by 2, let's say 1600 cycles, right? So if you receive an interrupt every 1600 cycles, you will not be able to even process the interrupt, right? Because the next packet arrives faster than you finished, because it takes you longer to process the interrupt, or most likely. Obviously, this device will never send an interrupt on every packet. There will be configurable interface, and you will say, send me an interrupt once in a while, and here's the buffer. But if you're switching to like 100 Gbps, those devices are so powerful that they will expose multiple hardware queues. And most likely, and I'm not an expert, but I'm guessing that you most likely will allow the device to send different interrupts, and they will be routed to different cores. And each core will be responsible for a specific queue, communication queue, right? And this way, this is where like all this knowledge of this IO epic and FLAPIC will become handy, because you say, look, maybe I can program the whole system in such a manner that, first of all, interrupts which are related to the specific queue will not be routed anywhere, because the queue is like with process on this core. The reason to do this is to make sure that the caps lines, which represents the queue, don't fly back and forth in this system, overloading this coherence link, but really stay here. And it's like, it's proven in many papers that it's a local processing of, if you start a packet and process it on a single core, it's usually faster than like starting on one core, switching to an application which runs on another core, and then switching back to the third core to answer with a reply packet, right? So the idea is to essentially carefully pin everything to a specific CPU, the interrupt processing, the application, and the device driver, and do everything on one core. That's usually faster. So again, if you go and program the last bits of performance, you will have to do something like that. I mean, if it's too much for now, that's fine. You don't have to remember, but just like remember that most likely you will have to dive into those mechanisms if performance is a question. Okay, any questions? Probably not. I bored everyone, so we have like 15 minutes. Let me quickly finish. Okay, but round robin is important, right? And finally, we kept talking about non-maskable interrupts. And again, they are always delivered through vector number 2, right? But the idea here is that CPU will always process a non-maskable interrupt, regardless of whether you like the state of the interrupt flag in the R flags register, right? So normal interrupts will be masked when interrupt flag is 0. NMI doesn't care, and NMI is a high priority, so it will preempt, as they say, nearly all other interrupts, but I don't remember which except, and which exactly, and will be delivered first through vector number 2, right? NMIs are always delivered at vector 2, and you cannot remap this, right? What the use cases in the, like, if you have error correction memory, for example, you can, like, a parity error will be delivered as a non-maskable interrupt. Typical use case in typical system, actually, I never seen a bug due to the error correction, but I mean, I'm not running a data center, so I never had to enough like exposure, but I imagine that if you're running your Facebook at the data center scale, sooner or later something will fail and you will get this ECC code, right? But typically what you will see is systems like Linux will configure a watchdog timer. And the watchdog timer will be delivered every so often, unless the operating system kind of like resets it for a later time, which means that, for example, somewhere in your scheduler, you say, look, I will reset a watchdog timer. And imagine now suddenly you have something like some condition which somehow blocks the system from doing a scheduling decision. For example, you have an infinite loop in a third-party device driver, which may be idle, right? We loaded it on Linux and it mostly works, but sometimes like runs forever and never lets anything else happen. And then when a watchdog timer is not, it doesn't get reset, so it actually gets delivered through a non-maskable interrupt. The OS gets control back and it can kill the process or thread which was running inside the network driver. So this is typically happens during development on Linux because you probably will screw something up. So you will see it watchdog. I don't know if you ever seen it, but it happens. Some debuggers use non-maskable interrupts. I never had a use case, but I only mentioned, remember I mentioned performance events, like those performance counter events typically delivered as non-maskable interrupts in order to increase precision of collection. Otherwise, you know, everything gets delayed and everything gets a little weird. And reliability condition, I don't remember what I meant here. So like again, so typically delivered through this local interrupt 1 pin. We configure it to be in non-maskable mode, but literally you actually you can program like the same keyboard interrupt as long as you say deliver it in a non-maskable mode, then it will be routed through vector 2. Interprocessor interrupts, which I mentioned earlier, like for TLB shutdowns, typically actually also are configured to be delivered as non-maskable interrupts. And again, the idea is to make sure that you react as fast as you can. Okay, one interesting thing is that, and I mentioned it before, but I just wanted to emphasize it one more time. So when the first non-maskable interrupt is delivered, right, subsequent non-maskable interrupts are blocked until you execute an IRAT. So for example, typically, if you taking an interrupt like a keyboard interrupt, and even if the interrupt descriptor table has a flag here saying disable subsequent interrupts, so you start executing the handler, interrupts are disabled, right? The moment you say STI, like essentially you set the interrupt flag in the R flag register, then interrupts are already in, can be re-enabled, and the next interrupt come in, and you can start processing, like, I don't know, timer interrupt, right? Another handler. But with non-maskable interrupts, it doesn't work this way. So you cannot re-enable the non-maskable interrupts. I think nothing will get delivered, neither maskable or non-maskable, until you execute the IRAT. It's kind of worth to remember when you program those. Remember, we talked about stack normalization and stuff like that. So it's like when you do an NMI, you have to remember when is that you can get the next NMI. As I was saying, you can configure anything as an NMI. So for example, if you want to configure a keyboard interrupt to be delivered as a non-maskable interrupt, if you run your LAPIC in this XAPIC system, there are like multiple versions or multiple interfaces which LAPIC exposes. I think we're going to be using XAPIC because it's simpler. There's a more advanced version which I'm most familiar with, but essentially you can say in the redirection table entry, typically it's like IRQ1 from the keyboard goes to pin number 1. So in the redirection table, you say for this entry, delivery mode is non-maskable. And then this field, which is a vector number, is ignored. It just says, okay, sure, always goes to interrupt in the IDT entry number 2, because it's a non-maskable interrupt, is routed to 2. Other fields still matter, but essentially vector doesn't matter. And so for sure, if you so want, you can reconfigure anything as a non-maskable interrupt. Okay, almost done, almost there. And we will be done with the interrupts forever. Okay, guys, so like main takeaways. LAPIC is per core, IOAPIC per processor. You have to configure both. This guy connects to external devices. This routes them to specific LAPIC things. This like routes into the interrupt descriptor table, right? So this allows you to say, go to core 0, go core 1, something, or choose the round robin policy. This allows you to say, go to interrupt vector number, something, right? Now, how do we configure it? Again, I'll give you the code which runs, but I still want you to have at least high-level story how these things are configured. It's not very interesting, and I mean, like, unless you start playing those games with like specific initialization of specific interrupts, remembering this distributed system figure, everything else is kind of more or less kind of boilerplate. So first thing is you have to disable the legacy programmable interrupt controller. Essentially, you initialize it, then mask all the IRQs by writing FF to this whatever register IMR, or put it in a special, this virtual wire mode, right? Okay, after the legacy PIC is disabled, you can start working on like enabling IOAPIC and LAPIC. So typically you enable local APIC. So each time you start a new CPU, remember we send it those, we'll put on a bootstrap processor, but then every time you initializing an application processor, you have to initialize the local epic. IO epic will be initialized only once, right? So you get this epic base register. Typically, it contains the field of like the address, which is here, but it's not strictly fixed. You set the bit 1 to enable LAPIC. Then you have to configure this spurious interrupt vector register. So essentially, you have to write some magical value, and then you have to essentially set the bit 8 to 1, essentially enabling it. Here you can like pick a vector. So essentially, the goal is to pick a vector for spurious interrupt. Otherwise, it will because it wants it to be configured. And finally, you kind of like initialize the IO epic. Again, it's memory mapped. You will get a specific memory region, and then you will go through those IRQ pins and configure the entry for the redirection table entries, essentially, which vector you want. So essentially, you go above like the first 32 reserved by Intel. Otherwise, you're hitting exceptions, although you can still do it, but let's see how it works. Like you have to distinguish page faults from external interrupts, possible but hard. You can pick a delivery mode, like, okay, sure, if we're picking fixed, then we will pick with the LAPIC number, like for example, 0, and everything will be routed to core 0, right? If we want something more adventurous, then we will pick this logical mode and stuff like that, right? Just a quick last 5 minutes. Actually, when do we end? At 20? Yeah, so last 10 minutes. But not much. So any questions? Let me stop for a sec. What I will give you is the source code, which does, which one? Atmosphere? Here. So something along those lines. So where are we? We already looked at it, but so essentially here we disabling the legacy programmable interrupt controller, like configure the interrupt descriptor table, get the IO epic base, init IO epic. Let's take a look at how we do it. So this is IO epic. And again, this code will be given, so like don't worry too much. Hopefully it will run. I mean, if it doesn't run, then it's a little. But essentially, there is some minimal magic which you have to essentially do here, which is what IO epic LAPIC. What do we have for LAPIC? So this is on the application CPU. Which one? This is on the bootstrap CPU. So we initialize LAPIC in this X-epic mode. Like here we set up the timer. Oh no, that's enabling the timestamp counter. This attach thing will what it will do, but essentially, essentially, probably you will understand how it works, and I don't remember myself, but those three things which we will have to do: IO epic, X epic, and then LAPIC. So here we don't forget that every time you write an interrupt handler, you will have to acknowledge the interrupt. Remember, we talked about it last time. So it's essentially the way for the programmable interrupt controller to know that you're done with an interrupt. So if you want to carefully understand what's going on, then it's doable, but more than like I kind of probably you can just run it and be happy about it. But just remember the story, how it goes. And if you want some funky setup, then I think everything is either available through those crates or declared here, where we have interrupt definitions, but essentially there is somewhere definitions of all these registers and stuff. Maybe I just missed them. Maybe, yeah. Not here, not here, here. Yeah, there's like various registers of the X epoch. So I think this is more or less it. So I think we are done with the interrupts. We started by saying, okay, we configure the IDT, GDT, TSS, all of it, right? So all of it has to be configured before you even touch the programmable interrupt controllers. Then you configure these two IO epoch and on each core LAPIC, and then you'll start getting timer interrupts. So I think more or less everything what I wanted to talk about it, I did, although it took me a while. But now that's probably it. So like again, I'm behind on homework because I'm like on some crazy deadline, which I'm falling behind, but I'll try to push it as soon as possible. But then after that, so homework will be kind of get to the timer interrupt, like set up IDT, GDT, everything, enable interrupt controllers to start receiving timer interrupt, maybe a keyboard interrupt as well. After that, we're good to go. Interrupts are running. We can send interprocessor interrupts to wake up other CPUs, so boot on all CPUs. But what we're gonna start talking about next time is we need to essentially construct the address spaces. So we will start talking about how to implement a memory manager to essentially construct a page table to map the address space. And then after that, we are kind of like running. We'll be able to construct address spaces. After that, we can load the code into ring 3 and start exit into user level and come back with the syscall. Okay, good. Sure. So then let me stop here. Any questions? All good? Okay. So yeah, thank you.